on how we could arrange and how we could design new materials that indeed would give us this 10, 11, 12, and a bit optimistic 17% solar cells. And then if there's time left, it might not be, but I can at least show you one or two slides. There's also ideas how to go beyond that 11, 12%. So we've seen that in polythiophene PCBM cells, there's quite a voltage loss from the optical band gap to the open circuit voltage. We lose quite something in the electron transfer. We lose something between the CT energy and the open circuit voltage of 0.4 to 0.5 volts loss. And we would like to do something about it. And of course, when we take this 0.4 and 0.4 to 0.5 volts loss from CT state to open circuit voltage as intrinsic loss in these cells, at least I haven't seen any good way on how to circumvent that at this point. In a practical way, then the only thing that we can really work on is this driving force and change that a little bit. And so in this material combination, there is quite an offset between these LUMO levels and also between the HOMO levels that causes maybe that the quantum efficiency is good, but at the same time, it causes a lot of energy losses. And so you can change that, and you can try to make more efficient acceptors, if you like, or acceptors that lose less energy. And one nice example of that one is this, where people have used BIS substituted PCBM by putting two of these substituents on the fullerene cage. You change the reduction potential such that the LUMO level goes up a little bit. That makes that the open circuit voltage goes up a little bit, and you can see that you get more or less the same current with an increase in open circuit voltage. And a similar approach has been done by using BIS indane fullerenes by Plextronics company together with NanoC. And there's also some work from, I think, from Yongfang Li's group in China on that work. So basically, you change the fullerene energy levels and you change the voltage. You can also increase the voltage, of course, by changing the polymer, and actually I've shown already an example of that. This is the polythiophene. This is this APFO3 drawn wrongly. This bond should be here. This is a mistake here. And they both have more or less the same band gap, but this has a much lower lying HOMO level now, so you don't work on the fullerene levels, but you work on the polymer level. You pull that down, and with the same band gap, you get more or less increase in voltage of 0.4 volts without changing anything in the band gap. The optical absorption spectra of the two systems are more or less the same. You just harvest a larger part of the energy. The efficiency doesn't really go up, and that is mainly due to the fact that the current goes down because of a lower quantum efficiency. And that is a bit problematic here. And also, these cells cannot be made that thick because the mobility is a bit less, and that makes that the fill factor is under pressure, if you like. So the fill factor is also quite some lower here, and that makes that this total cell doesn't help anymore. But at least you can change, by changing the energy levels of the materials, you can change the either the open circuit voltage or the current to some extent. So you can also ask yourself the question, what is now the maximum open circuit voltage for fullerene-based devices? Because we can predict that now, actually. And we know that the optical gap of PCBM is at 1.75 EV, more or less. If you take 1.75 minus 0.6, then the maximum open circuit voltage for any fullerene, or any, I should say, PCBM-based device is 1.15 volts, and otherwise it shouldn't work. If you look in the literature, you'll find the values of slightly over 1 volt. There's a number of papers that show that for these polymers, this APFO3, and now drawn more correctly, I think, yeah. And for this PF6T2, and we made this polymer that itself is not a very high efficient polymer. It gives you a 1% cell with a very poor fill factor. There's quite some current being generated, but we don't get it out at short circuit. But the nice thing about this is that it indeed gives an open circuit voltage of 1.15 volts. And I think that is more or less, maybe there have been slightly higher, 1.16, 1.17 volts. But that is indeed the maximum that has been achieved up to now for PCBM-based devices at room temperature under 1 cent conditions. and I doubt whether it's possible to make anything higher than that. And it shows, it's not to be pessimistic, but it shows that we are understanding what is happening in these cells. So if you want to make better cells, one thing that has received quite a lot of attention in recent years is making new polymers. It's making polymers that do absorb much more light and larger part of the solar spectrum compared to the initial materials as PPVs and polythiophene that absorbed up to 600, 650 nanometers. And the crucial thing is there to reduce this energy level, this lumo energy level, and not to raise too much the HOMO level, because then you lose voltage immediately. And if you lower this too much, you also reduce tendency for electron transfer. You have to carefully design that. And if you look into the literature, there is several recent results on all kinds of efficiencies. This is a bit a personal view at what has happened the last few years. Important materials were this one, made by Mats Andersson in Sweden. This material, made first by a Konaka company, also this is from Konaka, where they showed, this is a paper from Alan Hegel's group, where they showed 5.5% efficiency. These are materials that we have made. This is together with Bas F. This is materials that are also very interesting, coming from Looping's U groups in Chicago, and the Solama company in UCLA together with Yang in UCLA, giving higher efficiency, 6%, 7% recently. This is again from Konaka. There should be a nitrogen here. This is all kind of mistakes I see now. There should be a nitrogen here. But you can see that all these materials are developing, that some of them have band gaps that are interesting for more absorption, 1.6 here, 1.5, 1.4, 1.3. So people trying to make materials that give lower absorption coefficients. And these are not the best materials out there at the moment. I didn't collect. It's going so rapidly that you would need a day task to follow all the literature, what is happening. Just to show a bit on what we have been doing, not that that is better or more important than other work, but it's just because I had the slides and I can give you the message anyhow a little bit, is on these type of materials with diketopyrrolopyrrole units. That's kind of interesting unit with thiophenes. You can see here that in this material the absorption has shifted considerably, band gap of 1.4 eV, close to 900 nanometers absorption. C60 and C70, the blue and red one, again make a difference. C70 you absorb again more light, and if you optimize the cells well, you get the same fill factors and the same voltages. So really you get, because of this extra quantum efficiency, you get a bit extra current, and that helps in the efficiency. It is nice that you can cover a large part of the spectrum. What is not so nice about this total cell is that the total quantum efficiency is not very high. It's only 40%, and not 60, 70, or 80%. And that's why the efficiency got stuck at something like 4%, and it's not higher. It could be higher in this material if the quantum efficiency would be higher. It's even slightly more dramatic in this material, where it's very similar material, but one thiophene less, and the side chains are a bit different. The band gap has moved down, so you absorb even more of the solar spectrum. It's now 1.3 eV, but the quantum efficiency has gone down again. And this is, in many respects, an interesting material, but it's one of the materials that, in my view, is very close to being optimally designed. It doesn't work out to be optimal. It's an important difference. So it is, because we have now a material with a band gap of 1.3 eV, and the open circuit voltage of this cell is well over 0.6, close to 0.7. That makes that the energy loss from gap to open circuit voltage is slightly more than 0.6 volts. So it's very close to where it should be. Also the 1.3 eV, if we go back to the diagram that I showed you some time ago, this one is right on spot. This is this point. This should have given us an 11% cell, provided that quantum efficiency and fill factor was 65%. Now go back to this cell. And this is really, that is the material that should have given it, and it doesn't. And not because the voltage is not good, not because the fill factor is not good. Actually, we see C60 is quite good here. It's slightly less. It's in the right ballpark. But basically because the quantum efficiency is not 65%. It's only half, or less than half than that. And that makes that this cell doesn't get much more than 4.7%. But energetically, it's quite nicely designed, or came out quite nicely, I should be honest. And so we tried, of course, to design it to some extent, but it came out quite nicely. But still, it shows the problem. It shows that when you are trying to make something that is energetically optimized, you might start to lose quantum efficiency. And if you then move in the other direction, so if you move into higher band gaps, so less absorption, you indeed see that you can increase the quantum efficiency again, and you can get cells that are slightly better than the previous one, so over 5% in this case. And there's many variations in this theme that you can make. Important thing is that these efficiencies you can only reach, and that is not only for our materials, but for all the materials, for all what people call record cell or call hero cells nowadays, all the cells that give you 6 and 7 and 8, sometimes, very few, but some do, percent efficiency, that these high efficiencies, they need to have, first of all, the right materials, of course, but second, they need to be processed in the right way, again, to make this right morphology. As much as we have seen it with PPV PCBM or with polythiophene PCBM, you need to do something to make it work. And in this case, what we need to do is we use processing agents, as we call it. We add a little bit of a co-solvent, a high boiling solvent, that changes during the spin coating the morphology completely compared to when you don't use it. So this cell, these materials give you a 2% or 2.5% cell if you spin coat the polymer plus PCBM from chloroform. But if you add a bit of diodo-octane to that solution, you completely change the morphology. This is without the diodo-octane, this is with diodo-octane, and you make a very much increased efficiency. So you get to this 5.5 cell. And you can use a whole variety of these high boiling solvents. This is work from Sandra Kawai, so she's here today, and she has studied, for example, different of these processing agents, and you can see that depending on whatever, or irrespective of which of these four you use, you always come to the same efficiency and also to more or less the same morphology. I don't have a slide of that, but if you take the four morphologies that you get in these points for the four different co-solvents, they are very similar. You cannot distinguish them actually. You only see that depending on the type of co-solvent, an aromatic or an aliphatic one, you need quite different amounts of that. But the final morphology that you can obtain is more or less the same, and the final efficiency also. So that is an interesting development or interesting idea, that you use these co-solvents to change the morphology a little bit. How that actually happens, we are investigating it at present, and we're getting some ideas a little bit on how it works. Now, I showed you this 5.5% cell, and again, the analysis is similar to the one that I already discussed a little bit. Is where does it go wrong? It really goes wrong in the quantum efficiency. Yeah? Here we have a quantum efficiency on average something like 40%. In this material, the band gap to open circuit voltage loss is 0.7 volts. So we're on this curve, so we could expect something like 9%. The fill factor of that cell was 63%. It should be 65 to get 11. And you can see that if we would have had 65%, we would indeed have gotten very close to this 9% that you predict here. So again, energetically, this is not such a bad material. We lose slightly more than 0.6, we lose 0.7 volts. We could have ended up close to 10% if the quantum efficiency would have been right. And the quantum efficiency is not right. So are we doing something wrong? Yes. We know also a little bit what we are doing wrong, but we don't know how to solve it yet. This is a more difficult state diagram, in the sense that I have now drawn the ground state of the two, the polymer and the PCBM, the excited singlet states of both. This is a low band gap polymer, so it's a low singlet state. The triplet states of both, triplet separation here is small, but here it's large, and the CT energy. And we know the CT energy because we know the open circuit voltage of the cell. And the CT state has, of course, also a singlet and a triplet state. I draw them arbitrarily close together here. And then we have free charges. We don't really know whether they are really up here or down. They are somewhere here. So the energy level here, I don't know. But I know that I can measure it, or we can measure it, because we can see the spectral signatures of these charges. And these are two absorptions in the near infrared. And these are these two green lines. But we also see a third absorption, and that is this one, a red line here, and that is due to the triplet absorption of the polymer. So we see triplet absorption of the polymer, while we know that this state has not lived long enough to provide intersystem crossing to this one. So this triplet state is actually formed from the CT state here. So the CT state, in this case, produces free carriers. The cell works fine. It gives you a 5.5% cell, but not perfect. And some of the charges we know are recombining into this triplet state because we see this triplet recombination. Now this is actually, might be one of the loss mechanisms in these solar cells, that recombination to either the ground state or the CT state is occurring because the CT state here is not quick enough in dissociating into free carriers. So this process is hampered a little bit such that this process can take a considerable quantum efficiency. And that could be an explanation. We don't know how much this quantum efficiency is. It could be an explanation for the solar cell quantum efficiency losses. This is, so far, maybe it's not anymore the best published today, but one of the highest actually published today, work from Looping Yu and Solamar in Chicago and Los Angeles, respectively, where they've shown a 7.4% cell of this material and this C70 fullerene. And again, you see here diodo-octane as a co-solvent being used to optimize the device. And it's a very nice device with a good fill factor, close to 70%, current of close to 15 milliamps, and voltages over 0.7 volts. So it's a very nice cell, and you do see all kind of developments here happening recently. Okay, the last 15 minutes, I'd like to discuss a bit about tandem cells, because that is the new next thing, I think, in organic photovoltaics. Tandem cell itself is nothing new. It's well known in traditional inorganic solar cells, and you can also make organic tandem cells. Now, why would you want to make a tandem cell? It is because you can have a higher efficiency than this 31% from a tandem cell. Of course, in organics, we will not quickly get to 31%. I showed you that. It's more challenging to get there. But we can still definitely use tandem cells to make the cells that we now have more efficient. And the idea of a tandem cell is to use two subcells that you connect in series, and I'll explain that later, where one of the cells absorbs the blue part of the spectrum and the other cell absorbs the red part of the spectrum. If you optimize it correctly, this cell can give you a higher open circuit voltage than this cell. And that helps to reduce the thermal losses of the photons absorbed in this cell. Of course, you could make a same cell with only the small bandgap polymer that could also absorb these blue photons. But these blue photons would lose much more energy in the small bandgap cell to the open circuit voltage than they would lose in the wide bandgap cell. So by combining a wide bandgap and a small bandgap cell, you will increase the collection of photon energy. You will use the photon energy better, so to say. If you would only use this cell, then you could have the same good open circuit voltage for the blue and purple photons that you have now, but of course you would not absorb the red and orange photons. So the tandem combination really gives you an enhanced effect. And if you look at the Shockley-Queisser limit for a tandem cell, it increases from 31% to something like 42%. And if you go to a triple, it goes to 48%. And if you go on and go on and go on and go on, I think in the end you can get very close to the thermodynamic limit, actually. That is maybe not practical, but tandem cells or triple junction cells, or even higher, are definitely possible. Now, also organic tandem solar cells are not new. This is a paper from 1990, published in Chemistry Letters, a Japanese journal, where at that time already, more than 20 years ago, people made an organic tandem cell with a phthalocyanine and a pyrroline derivative, donor acceptor, a gold film in between, and another bilayer cell. So the Tang cell doubled, more or less, and it was shown that the IV curve, it's not brilliant, but the very important thing is you can make an open circuit voltage in this tandem cell that is more or less the double, not completely, but almost the double of the single junction cell. And that is what you expect. You place two cells behind each other. Basically, you place two batteries behind each other, and you expect the double open circuit voltage. So that is a nice demonstration. This was followed later by Steve Forrest's group, who used the same idea but made it more sophisticated and better, and got cells that properly worked. They still use a metal electrode here, and the big step came also from Karl Leo's group in Dresden, and we'll hear more about that in this conference from Moritz Riede, I think tomorrow in afternoon, on PIN junction solar cells, where they use doped semiconductors, so basically metallic organic materials, to make this connection layer. And here it was just metal, and here they use doped semiconductors for that. And still they use artificial gold layer in between. It's not maybe really necessary to use that. We will hear that tomorrow. And both cells give doubling of the open circuit voltage and have led the way to improvements. This is now used by Heliatech company in Dresden, and Heliatech is a company that is one of the current, I'm not sure if it's still world record of 8.3 tandem organic solar cell. This was one of the first cells that was made in Paul Blom's group with materials that we used, or that we made at that time. And Paul Blom and Afshin Hadipur made tandem cells based on organics, but still with an evaporated middle contact. So it was a polymer solar, the first polymer tandem solar cell, where one layer of polymer was solution processed, then you would evaporate the metal contact with a few layers in between, and then you would evaporate a second, or you would solution process a second polymer layer. We used the wide band gap and small band gap cell, and you can see that it nicely produces a tandem cell. Efficiency was not very high at that point. Important was then that we were focusing on this recombination layer, how to make a recombination layer that you can actually solution process all the layers, not only the active layers, but also the middle contact. The middle contact is important because in a tandem cell, it has to be transparent to light, of course. Light has to pass, and with metal layers in between, that is always a difficult thing because they tend to reflect and absorb some of the light, or quite some of the light. And the other thing that we try to do is, indeed, that you have to do, is to make the work functions such of these two materials that on one side it makes an ohmic contact to the PCBM, and on the other side it makes an ohmic contact to the next polymer, and there is usually a difference of maybe 1 volt between that, and in the middle don't lose any voltage. So how do you do that? Something that has two work functions at different sides, and no loss in the middle. And you can do that by making these two layers very conductive, so that the Fermi levels align, and that on each side the work function is still the same as from the material. And one way to do that is to use zinc oxide particles and P dot, and then you need a neutral, pH neutral P dot, because the acidic one would wash away the zinc oxide. So there's various challenges here. Is you need materials that have right work functions, good conductivity, good transparency, and then also not a trivial challenge is that you have to process all these layers on top of each other. And you have to make layers that do not wash away, or when depositing a new layer, you don't want to wash away all the previous layers. That is also not trivial. And then sometimes you need annealing or no annealing, and it's not easy to do that I can tell you. Now for this first cell, it worked. This was a PPV and PCBM cell, and we got a tandem device with not a very nice IV curve, voltage loss here, contact problem. That was solved by having some UV light, so that makes the zinc oxide permanently photoconductive, and you get to an open circuit voltage that is actually the same as the sum of the two subcells. This is the maximum power that we extracted from the cells. It was not an efficiency, just to show that it works and that you get a reasonable efficiency, or a working device, I should say. Then we moved on to make really a tandem configuration, and real tandem configuration, as I explained. You want to have a wide band gap material that has a high voltage, combine it with a low band gap material that has a low open circuit voltage, so it's here close to 1 and close to 0.6. This is a band gap of 1.4, this is a band gap of 1.9, and this helps to increase, they should help to increase the performance, because a photo of 1.9 eV would be absorbed in this cell, would give us a voltage of 0.1, of close to 1 volt, and if it would be absorbed in this cell, it would only give us 0.6. That would be 0.4 volts loss for that photon. So that really helps, and that really should help in increasing the performance. So we start off with two cells that are 3.6 and 4.2. This was the number published. We got this cell ourselves never better than something like 3.8. So slightly sub 4% cells that we can make of these. And then you can make a tandem cell. This is a TM cross-section of such a tandem cell. It shows all the layers: glass, ITO, P dot, first active layer zinc oxide, P dot layer, second active layer aluminum. This is this recombination layer that does a very important job in this cell. And then you can optimize the total cell. What you need to do is then, in a tandem cell, it's like with two batteries in any device, in a flash lamp or whatever. If one battery is going bad, or both batteries are going bad at some point, it's not enough and you have one spare battery to put in this one spare battery. It doesn't work. Because the second old battery cannot sustain the same current anymore. That doesn't help you. So you need to replace both batteries to get the same current. And in a tandem cell, much like that, if one cell would generate much more current than the other cell, then the balance is gone and the cell will not operate correctly. So to make it work properly, you have to more or less balance the currents. Not exactly. That is something that we found out later, that this balancing of currents is nice for inorganic solar cells, but not the prime design criterion for organic solar cells. It is slightly more sophisticated there. But in first approach, it is the idea to make both cells work in concert such that they help each other as much as possible in making a high efficiency. Now, if you do that, you can play around with the two active layer thicknesses. That's the only thing that you can change a little bit. You have chosen your materials. So the only thing that you can really change is the thickness of the two active layers. Maybe that Morris Reader tomorrow will tell you that they can also play around with the thickness of the recombination layer. For us, for other reasons, that was not so much a choice, because if we make them thicker, we have quite some resistance in there, so we would lose fill factor. So the only option for us was to change the thickness of these layers. But that works very well. There's actually no problem with that. There's also no disadvantage of that. So you can play around with the two active layers and you can optimize current, voltage, fill factor, and the total efficiency. And we ended up with a prediction that if we make the right tandem cell, and this is a simple slide, but it's actually the first time it was a lot of work. Also now still it's a lot of work to measure the optical constants, to measure all the single layer device here. To make this 4 graphs, you need quite a few months of work usually to get that. But then once you have it, you know what to do. And you need to make this cell. And if you make that cell, you actually get your improvement. So you get we measured the tandem cell of close to 5%, whereas these were the values that we predicted that this cell would give at these thicknesses. So you see that the correspondence is quite good. It's a working tandem cell. It gives the right open circuit volts, the right fill factor, the right efficiency. Especially the fact that the fill factor is more or less what we predict means that the recombination layer works without too much resistive losses. Also, there is no voltage losses because the voltage is nicely predicted. So that gives a nice idea. And you can also make slightly larger devices. This is the first was a 4 by 4 millimeter. This is a 10 by 10 millimeter cell that also works. So that is a nice step, I think, towards using different bandgap materials to make a new cell that has a higher efficiency. Of course, this is not yet a record high efficiency, but eventually this will happen once we can incorporate better and better materials into such devices. So if we come back to materials that gives us 6, 7, 8%, and we would have one wide bandgap and one small bandgap, then we would definitely be able to put that into a tandem that gives you an improved efficiency. And then you should think that if you are realistic, that if the maximum of a single junction cell would be 12%, and we would have 2 of them, then we could raise the efficiency of a tandem cell maybe to 15% or something. So you cannot really double it. You cannot simply add them, of course. They just eat up each other, parts of each other's spectrum. But you can definitely get an increase of up to 30, maybe even 40% compared to the single junction cells. So that is an important step. Okay, I come to my last slide. A lot of people, I presented a lot of things, and I have to apologize that most of the things that I shown were data that came somehow out of our own lab. While I know that there's many, many other people that made very important contributions, but I don't have all their slides, so to say, so I focused a bit on our own work, but I hope that I've given you a bit of an overview of what is happening in organic solar cells, where it's going towards. I think that the progress has been much because we understand quite a lot of these cells now from device point of view, from morphology point of view, from photophysics point of view, from fundamental point of view. We understand what we want. We're getting close to really understanding what is happening. We need still new materials. The real progress in this area in terms of efficiency has only come, I would say, from new materials, from better materials, from the people that are in the lab synthesizing every day something new and trying to make something better than they had before. And the trick of making tandem devices is something that is obvious if you think about solar cells itself, but requires still some thinking. Especially for us, this recombination layer is still causing us some headaches so now and then. It works nice in the examples that I've shown. I can also show you some examples where it doesn't work. And so that really needs some further investigation. But I would like to thank all the people that contributed somehow. I hope that most of the names were on the slides that I showed, and that I hope I didn't forget too many names here. But it's a very important work in materials. Initially, Johan Bijleveld, Arjan Zoonveld, Melanie Verstrijden did quite a lot of the work that I showed. People in the device area, I would say, Jeroen van Duren was a first PhD student making solar cells. He actually made his first cell in the previous century, actually. Was a few days before Christmas, 1999. And then a lot of people followed from that, making Jan Gillois was very important in making these tandem devices. These people did photophysics, especially Paul van Hal, Ton Offmans, Dirk Veldman, Daniele now did important work. Clara and Martin Kimmering did a lot on the AFM and the modeling. And the group of Joachim Loos, he's now in Scotland with Xiaonu Yang, he's now in China, and Svetlana van Bavel, she graduated, did important work. In Groningen we had a lot of collaboration with Kees Hummler and Paul Blom and all their collaborators that did important work. I'd like to thank also people from BASF, Mathieu Turbier, TNO, ECN in the Netherlands, and funding Interreg, of course, they finance our project. And with that, I'd like to thank you also for your kind attention.